Hi everyone, welcome to Stats on the Weekend with me. So I wanted to spend this time to really clarify how to find the confidence interval for a chi-square distribution. I'm going to skip some steps a little bit just to sort of get right down to the point, but I'm going to try to create some other videos that sort of hint at those steps when I get the chance. So first, let's talk about what the chi-square distribution and how we're using it is. For us, the chi-square distribution, just to start off, you can think of it in many respects as a distribution taking all the different possible sample variances that we can find of a particular population variance that we will never know. And you will never know this. You can guess at it, but you'll never truly know what that population variance is. Second, because we never know, we can take our next best estimate or the sample variance to try to predict what that population variance is. But that's not enough. If we're trying to predict that true population variance in order to establish a confidence interval, we have to take, let's just say for argument's sake, 96% of all the possible sample variances that are out there, as represented by our chi-squared. Meaning there's 2% here and 2% here. Now, I'm skipping a couple of things. And so I want you to either talk to me or go back to previous videos and understand why variance cannot be negative. I want you guys to talk to me or go back to previous videos to understand why this is how we set it up to find the confidence interval or what's really happening here. But in short, this is sort of the same method that we used when we're finding the confidence interval for sample means. We're applying the same method to finding the confidence interval for variances. Now, a couple things to remember. You got to start with remembering what the chi-squared formula is, which I'm writing right there. But you also got to understand how we need to set this up. If we want, as our confidence interval, 96% in the middle, we have to find the chi-squared of there, which represents 98% to the right. And we have to find the chi-square of there, which represents 2% to the right. Now, if we're setting this up mathematically to get 96% in the middle, it's really the chi-squared of 98% to the right less than or equal to whatever this is. But we just can't use s squared. We have to compare on like or similar values. So we got to make this chi-squared. And in this case, since we have no numbers for our sample, we don't know what that is. So we're going to put our next best formula for that, which is our chi-squared formula. That's going to represent our population variance in chi-squared units. And then we do the chi-squared of 2% to the right. Now, what I want you to understand from this and how we set it up, this is chi-squared, this is chi-squared, and this is chi-squared. This formula in the middle gives us a chi-squared unit representing our sample variance. This is how we set it up so that you can compare along chi-squared units what exactly is 96% in the middle and 2% on the tails. Now, this won't help us because we don't have a predicted variance in the middle. We need to find that somehow, because our predicted variance in the middle, or this, is going to be in the end predicted by S squared, or our sample variance. So this is how you solve it. You take it apart bit by bit. So we're going to do this side first, and doing the math, you get x squared 98%. You get this formula. Then solving it, you get the theta, or your population variance that you're predicting, is an n minus 1 times the sample variance over the chi-squared with 98% to the right. Let's do the same thing on this side. Now, you get n minus 1 s squared over theta variance is less than or equal to x squared 2% to the right. Or you flip them, it's n minus 1 that over x squared chi-squared 2% to the right is equal to the population variance we're predicting. Putting these two together now into one cohesive whole, where we can actually use it to make a statement about confidence intervals. We bring this to the right, and we say the population variance we're predicting is less than or equal to n minus 1 over s squared, what I'm writing basically, over 98% to the right. And then on this side, it's n minus 1 squared over chi-squared with 2% to the right. What I want you to notice in how we set this up now is we did the same thing as we did before with means. But if we're setting up the math appropriately, we have to compare along the same chi-units. So remember, this is a chi-unit, this is a chi-unit, this is a chi-unit. We're comparing 96% along the same chi-units. And then notice what happens. If we solve this so that we are actually saying that our middle value represents our point estimate, which is s squared, or what we're predicting, which is the population variance. Just like confidence intervals, our middle value in a confidence interval is our point estimate, our value that we care about. So if we solve that to get this in the middle, we end up with something where here is the clincher, where your chi-squares are flipped. So let me highlight that instead of cross it out. And here's the interesting part. Your chi-squares are flipped when we solve for actually having a point estimate in the middle. So when we go back to our graph up here, and I erase your highlights, my highlights, your chi-squares, no longer is this representing your upper bound. You actually have to put that math on the lower bound numbers, which I'm scrolling back down. It's right here. No longer is your 98% representing your lower bound. You actually have to put that math back on your upper bound and use that number for your upper bound. Yes, That's the chi-square number where, yes, if we were to redraw those chi-square numbers, that 2% represents the chi-square number right there. And that 98% represents that chi-square number right there. But because of how the math works, because this distribution is only positive, we have to flip them in when we calculate the confidence interval. And so this will end up with some number that's low because this chi-squared number will be of 2% will be very high. And so when you divide by a high number, you get a low number. This will be a higher number. And it's because this chi-squared gives a lower number. So I hope that made sense, because the struggle that a lot of people will face is that they won't recognize that when you're doing the math, these flip on you. And so no longer is your 98% to the right really representing your lower bound. In the math, it has to be a part of your upper bound. And you can actually rewrite the confidence interval equation that you use with the chi-squared formula. You can rewrite it to look like this. And let me just make sure I get the math right. You can rewrite it to look like this. Your lower margin of error is going to be your n minus 1 times that over the chi squared of your upper. Your upper margin of error is equal to n minus 1 of your lower, and your point estimate is equal to your sample variation. And there, I believe we've covered it. Feel free to ask me any questions you have. Again, what I'm trying to illustrate is the chi-squared distribution works differently than the normal distribution for the means, because we're dealing only with positive numbers. And in that case, the math works out so that this 98% flips over there, and then this 2% flips right back in terms of what we are using for the actual calculations we make. I hope this was helpful, and thank you.